No, she means that you study with other people because you're the one that made 103 and everybody else.
All right, let's get started. Okay. So today we're going to finish up Chapter 5 on stereochemistry. Okay, and then move on a little bit. Okay, so we got one major topic left in here. And that's the topic of optical activity. Okay. So this is an important topic because this is going to be the way to distinguish between enantiomers. Remember we said last time that enantiomers had the same physical properties, same melting points, boiling points, and so on. Okay? Optical activity is how we're going to distinguish them. So let's start off by looking at something called plain polarized light. Okay? So let's pretend we had some kind of light source here. Okay? Some kind of light bulb or whatever. And that light bulb was giving off a bunch of waves of light. Okay? So they're coming off in random directions. And we can characterize each wave of light by this double arrow. Okay? What that's doing is depicting the plane of that light. Okay? The plane of the amplitude of that light. Then what we're going to do is stick in front of this light source this thing here, okay, that's called a polarizer. Okay. And if you look, this polarizer has this dotted line down the middle. That's called the axis of polarization. Okay. So what this polarizer is going to do is it's going to act as a filter. Okay? It's going to filter out some of these light waves. Okay? The only one that it's not going to filter out is the one that has the arrow parallel to its axis. So the only one that will come through is one that's like that. And that particular wave that comes through is what's called our PPL, which you got it, stands for plain polarized light. Okay? So this is the definition of plain polarized light that we're going to use in our topic today. Okay? Any questions what plain polarized light is? Okay. All right, let's go to the second spot. And look at something called a polarimeter. Okay? I'm going to leave this here. You'll probably have to redraw all this under the second heading. So I'll give you a couple of seconds to redraw that. Okay, so polarimeter is going to have the same setup and a little bit more.
Is there also a polarizer in this portion?
Mm-hmm. You okay? Okay, so what's additional here in the polarimeter is now we're going to have this tube here. Okay, this glass tube. And inside the tube, we're going to have a solution of chiral molecules. Okay? So there's our solution of chiral molecules. And now, what this plane polarized light's going to do, it's going to shine through the tube. And what it's going to do, it's going to interact with these chiral molecules so that when it comes out on the other side, it's going to come out key point rotated. So that's what chiral molecules do, is they rotate plane polarized light. Okay? And we say that something that rotates plane polarized light, it's optically active. Optically active. Okay? So there's a lot of definitions there. Okay, so chiral molecules are optically active because they rotate plane polarized light. Okay, and if we were to draw a line matching that original axis of polarization, we could then measure the angle that that plane polarized light rotated. And that angle we will call alpha. Okay? So alpha degrees is called the angle of rotation of the PPL. Lastly, what we do in this polarimeter is we have another polarizer here. Okay. And we have our eyeball here. Okay. It's a big pupil. Okay. So what we do is we look through this polarizer and see if any light is coming through. Okay. So follow me here. Make sure you're getting this. If this plane polarized light coming through did not rotate, then what? Would any light get through this polarizer?
No.
No. Okay, because they're blocking each other out. Okay. So if it didn't rotate plane polarized light, then I would see a dark field. I would see a dark field. But if it rotates plane polarized light, I'll see some light. Okay. Then I would have known that I had a solution of chiral molecules. Okay? And what we do with this polarizer is we can rotate it to figure out what that alpha was that it rotated. Okay? Hope you guys got that down. Okay, so this is the setup of a polarizer. Okay? Well, let's go ahead and add some extra definitions to this. Our alpha value can be one of two signs. It can be positive or it can be negative. Okay? If it rotates in the positive direction, they say that it was dextro-rotatory. Okay? So dextro-rotatory is positive, levo-rotatory is negative. Okay? Dextrorotatory will sometimes symbolize by D, and levo will symbolize by L. Okay? Okay. Let's take it a step further here. When we report an alpha value, we'll report it in brackets, and we always report it with different parameters. We report it with the temperature, concentration, and L. This L stands for the length of the tube that was in the polarimeter, the length of the tube. Okay? So an alpha value varies depending on the temperature of the experiment. So I have to report what temperature I did. It varies on the concentration of the chiral solution. If I have a dilute or concentrated, that will change the alpha value. And it also depends on the length of the tube. Short tube, long tube, that'll change the alpha value. So I have to report all of these so that somebody wants to repeat the experiment, they know what parameters I did it under. Okay? Okay, so let's start seeing how this can help us with enantiomers. Okay? Okay, let's say we had a pair of enantiomers. We'll just call them 1 and 2, whatever they are. Okay? Let's suppose I took number 1 and I looked at it in a polarimeter. That way I can measure what its alpha value was. And let's just suppose that came out to be a positive 20 degrees. Okay? I have no way to predict that that was 20. I have to measure it. Okay? Just wait, you know, I have no way to predict how fast you can run a mile. We would have to go out and measure it. Okay? But once one enantiomer is known, guess what? Now I can predict the other enantiomer. It'll be what? Equal but opposite sign. Okay? So if this is plus 20, that will have to be negative 20. Okay? If this was negative 20, that would have been positive 20. If this was negative 5, that would have been positive 5, and so on. Okay? So you see how enantiomers work. Okay? And there's no correlation between R and S. If one was R, some R's show up positive, other R's show up negative. There's no correlation between those. What do you have to do? You have to measure its optical activity in the polarimeter. Okay? There's no other way around it. Okay? So any questions on how enantiomers are measured? Okay. Well, let's look at something else then. Let's suppose I had an achiral molecule and I put that into the tube. What do you think the alpha value for that would be?
0.
What's that?
0.
Why 0?
Because you said all the chiral molecules are rotating.
That's right. Okay. So any achiral molecule, alpha value will be 0. Okay. So polarimetry is an easy way I can tell if I have a chiral molecule or an achiral molecule. Okay? And since the alpha is 0, we then say it's optically inactive. Okay? So optically active is only if it rotates plane polarized light. Okay. Let's look at one other thing about optical activity. Okay. And that's the thing of mixtures. Okay. Let's look at some mixtures here. And let's suppose we had a molecule that could be either R or S. Okay? So here's the R enantiomer, whatever it is. Here's the S enantiomer, whatever it is. And at these extremes, let's say we have 100% of the R and 100% of the S down here. Okay. And let's say that the R had an alpha value. Let's make up one. Okay. Let's say that the R has an alpha value of plus 10. Well, if I know that is, what does the S have to be?
Negative.
Negative 10. Okay? So 100% of R gives me this, 100% of the S gives me that. Now what we want to do is look at mixing somewhere in between. Okay? So let's pick a mixture. Okay? Let's maybe pick a mixture here where maybe I have 60% R and 40% S. Can I calculate what the alpha value would be? Let's see if we can do that. Okay? So my alpha value would be 60% R, so 60% is 0.6 times its alpha value, which is 10, plus 40% of the S, which is 0.4, times minus 10. And what would that add up to?
2.
Okay, plus 2. Be able to do that in your head. You shouldn't have to pull out a calculator for that. Give me a break. Okay. So does that value make sense? Yes, because I got more R than S, so my net alpha value better be positive. And sure enough it is. Okay. Any questions how we did that particular mixture? Yeah.
It's 50-50.
Well, that's what we're going to do next. Don't ruin the surprise. Any questions on that calculation? Okay. So let's go ahead and do a 50-50 mixture. If you do the math real quick, what do you think the alpha value comes out?
0.
What do you think?
It's gonna rotate one way and rotate back.
What do you think? What do you think?
0.
Okay. So you can do the calculation. 0.5 times plus 10 plus 0.5 times minus 10, you get 0. Okay? Or you can, like you said, I got equal amounts so they cancel each other out. That's exactly what's going on. Okay? So this is a second way to get an alpha value of 0, is if I have a 50-50 mixture of 2 enantiomers. And this particular mixture has a special name. It's called a racemic mixture. Or sometimes called a racemate. Okay. So, is a racemic mixture chiral? Is it chiral?
Yeah. No.
Yes. Okay, the R is chiral, the S is chiral. It's just the mixture, that particular equal mixture, that's giving the alpha value of 0. Okay? So that's one way to get 0. The other way is to have an achiral molecule. Okay? Any questions on polarimetry or racemic mixtures? Yeah.
Is that the only 2 ways you can get 0?
That's right. Okay, so that finishes up stereochemistry. Okay, took us a few lectures to get through it. Okay, but I think we came through it unscathed. Any questions on stereochemistry in general before we move on? Okay, so we've covered a lot, all the way back with definitions of enantiomers, okay, all the way to optical activity, okay, all the way to racemic mixtures, which are what? What's the definition of a racemic mixture?
A chiral mixture that it still has an optical activity of 0. So, what is it?
Half Less than half our molecules are the same chiral carbon, or chiral molecule.
Okay. Okay, you guys are getting there. Let me give you a condensed version. It's a 50-50 mixture of two enantiomers. A 50-50 mixture of two enantiomers. Okay? Because the molecule could have more than one chiral site, right? And so it's got to be two enantiomers. I just did the simplest enantiomer, just an R to an S. Okay, well, this gets us into the last part of this section. Done with chapter 5. So what are we going to head into next? Chapter 6. Okay, chapter 6, there are many topics. For this exam, we're only going to cover half of chapter 6. Okay, then the other half of chapter 6 will be in the other exam. Okay, so if you look at your outline, that's why we call this chapter 6A. Okay, so many topics in chapter 6. The first topic we're going to look at is that of alkyl halides. Alkyl halides. What do you think alkyl halides are?
Alcohol and halogens.
That's how.
Okay, alkyl groups with halogens. Okay.
Removal of one hydrogen from alkanes
Replacing halogen.
or 1 to 2 halogen.
2 halogens.
Okay. Or you could have 2 halogens on there, or 3, or however many you want. Okay. So that's exactly right. So let's go ahead and start looking at some of these. Okay, so here's some simple ones here. What do you think the name of that one is? Okay, chloromethane. Okay, so very good. So that's how we name these halogens: chloro, bromo, fluoro, iodo. Okay. But it turns out to be another way to name that. Remember from general chemistry what the name of that was? Sodium chloride. So here we named it as a chloride. Same thing down here. That forces the CH3 to be a methyl group. So we can call that methyl chloride. Okay? So you got to be familiar with both ways. What's one way to name this molecule? Okay, you could do ethyl chloride or chloroethane. Let's go on to something like this. What do you think the name of something like that would be? Star.
Isobutyl bromide. Tertiary.
Somebody give her some help.
Tertiary butyl bromide.
Okay. So this would be one way here. T-Butyl Chloride.
Where you get chloride from?
Or bromide. Thank you. Okay, use the chloride so much that you get stuck with it. Okay. So T-Butyl Bromide. Okay, so don't forget your T-Butyl group here. What would be another way to name that?
T-butane.
Butane.
But you, Hot, how would you name that? Give us some help, Hugh.
I would name it. Bromo.
Bromo,
Bromide.
methyl,
Okay. So you gotta find the parent chain in here. So what do you got?
methyl bromide, propane.
Two bromo, two methyl.
Methyl bromide.
Ethane. No, I'm just one. Oh, okay, so two bromo, two methyl. Ethane. Oh, it's
Propane.
propane. Oh,
Okay, 3 carbons
my bad.
for propane. Got it, Scott?
Yeah, I got it.
Okay. So don't forget these isomeric groups, the T-butyl, isobutyl, sec-butyl. Okay? That's something like this here. Let the green cap have it now. Let her answer this one. Don't anybody help. What's one way to name that one?
2-iodine. 2-iodine propane.
Okay, that's one way. Two iodo-propane. What's another way?
Purple iodine.
We'll go with 79 back there. What's another way of naming it? What kind of group is that?
Isopropyl.
Very good. Isopropyl. Isopropyl iodide. All right, so you want to be familiar naming them both ways, okay? So this way here are what we call alkyl halides. See that?
Well, regardless of how we name them, they're still alkyl halides or no?
Oh, yeah. But the second way, you're naming it as an alkyl halide. Okay, let's look at these molecules here. Let's look at naming these ones. Okay, so we already saw how to name the first one. Methyl chloride. Okay. What will be the name of the second one?
Methyl dichloride?
Okay, so you could call it dichloromethane, right? Okay, so one carbon is methane. You've got two chloros there. Well, this one here introduce you to this CH2 that's sometimes called the methylene group. And so you could also call this methylene dichloride. Okay. Sometimes it's abbreviated MECL. Okay. This one here, what's one way to name that one? Trichloromethane. Very good. Okay. But this also has a trivial name. Called chloroform. That's what they used to knock people out with. Okay. Chloroform's very bad for your body, very cancer-causing. Destroys the liver. Okay. If you ever work with chloroform, make sure you wear good gloves. You don't want it on your skin. This last one, what do you think you call that one? Tetra what? Tetrachloro what? Methane. Tetrachloromethane. Okay. Or it's most often called carbon tetrachloride. Okay, or sometimes called carbon tet for short. Okay, another very toxic molecule, very toxic. Okay. In fact, when you start putting halogens on molecules, very toxic. Make sure you don't touch them, smell them, or anything. Work with them in the hood. Bad news.
Don't they make artificial sweeteners with chlorides in it?
Yes.
That's not good for you.
That's why I don't take them. Plus other reasons. Okay? It's always best just to use regular sugar, okay? Or even better, no sugar at all. How's that? People think since they're drinking Diet Coke, they're getting away with it. No, they're just making it worse. Bad. Any of those fake sugars, bad news.
What about Splenda?
Bad news. That has chlorine. They get big bags of it too at Walmart. People just get fooled. Okay? Well, when they get 60, 70, start getting cancer. See what? Okay, so just eat as natural as you can. It's the best way. Try these false things. All right, well, let's go ahead and stop there for today.